So the following video will be how to implement a partition coefficient in COMSOL. So what we have here is, let's say we have oil on the bottom, water on top, and a partition of some molecule between the two phases at this interface. So to do this, what you actually need is two transport dilute species for the same concentration of the drug. So the first thing you should do is have as many dilute species as you have drug in different phases that get partitioned. So how we're going to do this partition example is we're going to make a concentration for the bottom. So for the bottom phase, we're going to call some concentration C bottom. And for the top, we're going to have some concentration called C top. Now this is the same molecule, but in two different phases, and so it's essentially two different species, but it's the same species. So to do this in COMSOL, we are going to, So we need to specify some flux at this boundary condition. We're going to do a stiff spring approximation in COMSOL. Okay, so the stiff spring is you're going to add a flux for C bottom, and it's going to be some spring constant times C bottom minus C top. Okay, but where's the partition coefficient now? Okay, so we're going to define our partition coefficient this way, where K is the partition coefficient and there's some separation between the molecules in the different phases, C bottom, C top. So for this example, I'm going to use K equals 0.5. So C bottom will equal 0.5 times C top. So we're going to multiply the C top by 0.5. Why do we multiply the C top by 0.5 and not C bottom? Because K has units of C bottom over C top. Just go back to this. So C bottom over C top, and so that way units are canceling. Now we're going to do the same thing almost for the C top phase. So we're going to add a flux. We're going to put it on this boundary, and we're getting 1,000. Now for nomenclature, we're going to put C top over here and C bottom, and then we're going to bring the partition coefficient over here. So for the flux, it should always be the species in the domain that you're studying minus the concentration in the other domain. So for this, it's C top, and so I'm always going to have C top minus whatever else. And then the spring constant, it will vary based on the problem. The higher the value, the sharper the interface. The lower the value, the less sharp. Okay? So for both domains, I'm going to have an initial value of 1.5. And this way I should get a 1 to 2 ratio when I'm all through. And for this problem, I'm just going to arbitrarily pick a diffusivity that makes the problem look good. I'm going to solve it for 100 hours, 3,600, and I'm just going to use a finer mesh. So build all, and I'm going to click compute. Okay, so what I should see now is if I have I should have a concentration of 2 on top times the partition coefficient of 0.5, and I should have 1 on the bottom. So I should have total of 3 with 2 on top, 1 on bottom. Okay, but what do I see in my plot? I can only see C bottom. I can't see C top simultaneously. So what we're going to redo then is we're going to go up to definitions. We're going to add variables twice. So variables 1a, we're going to do domain. We're going to do the bottom. And we're going to call some C bottom. We're going to go to variable 2a. We're only going to select the top. We're going to call C top. Okay? And then we're going to come back here and recompute real quick. And this way, now we can plot concentration and see both simultaneously. So instead of plotting C bottom or C top, I can plot C, and what do I see? Sorry for the pun. I see 2 on top and 1 on bottom, which correlates well with K. So I'd have 2 times 0.5 gives me 1. Okay? And if you want to see how it changes over time, we can add a 1D plot group, line graph. And I'm just going to select one of the boundaries. I'm going to select C. I'm going to click plot. What do I see? Everything starts off at 1.5, and the bottom decreases down to 1, and the top increases to 2. So let me recap how to do a partition coefficient. So you're going to have a transport dilute species for each phase, and you're just going to give it some arbitrary concentration. And then in your variables, you're going to specify for each domain, and you're just going to give it just some concentration name for both. This way you can look at it all at once. And then for the flux, you're going to have some spring constant times first the concentration in the domain you're in minus the concentration it's going into, and then the partition coefficient will go with either variable based on how you defined it. So if I switched C top and C bottom, I would multiply the K over here first. It's just convention. Everything should cancel. Units should be consistent. That's all there is to it. Thank you, and this is how to do a partition coefficient in COMSOL.